Hello everyone! In this lesson, we'll cover Section 1 of the Logic Design Review. Specifically, we'll go over what logic design is, what Verilog is, and what logic gates are. So, what is logic design? Well, logic design is what allows you to design digital circuits. More specifically, it's the process of combining basic building blocks, called logic gates, into larger circuits that perform a specific function. With logic design, you can take an idea or algorithm and implement it directly in hardware. For example, a calculator is just a digital circuit that executes mathematical operations, and that circuit can be represented as a schematic made of interconnected logic gates. Knowing how to connect those gates together to build a fully functional piece of hardware is what logic design is. The image below shows an example of a simple digital circuit built by connecting multiple logic gates together. So, what are logic gates? Well, gates are the basic building blocks of any digital circuit. There are only 7 fundamental logic gates, and the table below shows all of them. This table shows the 2 input versions of the gates for simplicity, but in practice every gate, except the NOT gate, can take 2 or more inputs. Each gate still produces a single output. By combining these gates in different ways, engineers can build extremely complex hardware. CPU, GPU, and AI accelerator chips are ultimately just massive digital circuits built from billions of these simple gates connected together. Let's now go through each of the 7 logic gates, one by one. We'll start with the logical AND gate. An AND gate takes in 2 or more binary inputs and produces an output of 1 only when all inputs are 1. If even one input is 0, the output becomes 0. In example 1, we have a 3-input AND gate. What will its output be? Well, since all inputs to the gate are 1, the output is 1. What about example 2? In example 2, since there is a 0 present on one of the inputs, the output is 0. Also note that when we say 1 and 0, we are really referring to voltage levels. A logic 0 is typically near 0 volts, and a logic 1 is near the supply voltage, like 3.3 volts or 5 volts. The exact voltage levels depend on the hardware, but the idea is always the same. One range of voltages is interpreted as 0, and another range is interpreted as 1. So, in these next 2 examples, what do you think the output of the logical AND gates will be? Remember the rule. The output is 1 only when all inputs are 1. Otherwise, the output is 0. Go ahead and pause the video to try it yourself. Hopefully you already attempted it on your own. The outputs are 0 for example 3, and 1 for example 4. Let's now discuss the logical OR gate. An OR gate takes in 2 or more binary inputs and produces an output of 1 when at least one input is 1. It only produces an output of 0 when all inputs are 0. In example 1, we have a 3-input OR gate. What will its output be? Well, since there is a 1 present on one of the inputs, the output is 1. What about example 2? Well, in example 2, there are also inputs equal to 1, so the output is still 1. The only time an OR gate outputs 0 is when every input is 0. So, in these next 2 examples, what do you think the output of the OR gate will be? Remember the rule. The output is 1 when at least one input is 1. The output is 0 only when all inputs are 0. Go ahead and pause the video to try it yourself. Hopefully you already attempted it on your own. The outputs are 1 for example 3 and 0 for example 4. Let's now discuss the logical XOR gate. An XOR gate produces an output of 1 when an odd number of inputs are 1, and an output of 0 when an even number of inputs are 1. In example 1, we have a 3-input XOR gate. What will its output be? In example 1, there is only one input that is 1, which is an odd number of 1s, so the output is 1. What about example 2? In example 2, there are 2 inputs that are 1, which is an even number of 1s, so the output is 0. So, in these next 2 examples, what do you think the output of the XOR gate will be? Remember the rule. The output is 1 when an odd number of inputs are 1, and 0 when an even number of inputs are 1. Go ahead and pause the video to try it yourself. Hopefully you already attempted it on your own. The outputs are 0 for example 3, and 1 for example 4. The logical NOT gate is the simplest gate of all. It takes in a single input and outputs the opposite value. Because of this, there are only two possible cases. In case 1, the input is 0, so the output becomes 1. In case 2, the input is 1, so the output becomes 0. The NOT gate is also commonly called an inverter. Now let's cover the remaining three gates: NAND, NOR, and XNOR. These gates are not fundamentally new. Each one is simply the inversion of a gate we already discussed. In other words, you can think of them as taking the original gate and then placing a NOT gate on its output. For example, a NAND gate behaves exactly like an AND gate followed by a NOT gate. That's what this diagram is showing. The NAND symbol on the left is equivalent to an AND gate whose output is inverted by a NOT gate on the right. The same idea applies to the other two. NOR is an OR gate followed by a NOT gate, and XNOR is an XOR gate followed by a NOT gate. So if you understand the original gates, then these other gates use the same rules, plus an inversion at the end. So, we've now discussed what logic design is, and we've gone through all 7 logic gates. We can now discuss the final topic of this lesson, which is what is Verilog. Well, Verilog is a hardware description language that allows you to describe digital circuits at a high level. Instead of drawing out every gate by hand, you can write Verilog code that describes the behavior of the circuit, and then computer tools translate that description into real digital hardware, which automates a huge amount of circuit design work. Even with that automation, designing robust Verilog systems is still very difficult. For that reason, at the time of recording, AI has had effectively no impact on hardware engineers' job security. One of the most important skills that enables a hardware engineer to write strong Verilog is the ability to do logic design by hand. Engineers who understand logic design deeply are the ones who can build the robust, difficult Verilog designs, which is exactly the kind of work that automation and AI still struggle to do reliably. In the first half of this course, you'll learn everything you need to know about logic design. Then, in the second half, we'll take that theory and start implementing real digital circuits using Verilog. In the next video, we'll begin with the fundamentals of logic design. We look forward to seeing you there.